Hey everybody, before we dive back into today's engineering Good morning. This is Jazz. I'm at Rebel Engineering and I'm doing something a little different. This is going to be my first time doing a live question and answer. Usually I make videos ahead of time and post them, but I want to try something a little different. I have a pretty extensive background in mechanical engineering design and manufacturing. I have a degree in mechanical engineering from Purdue University. And today I'm going to start out doing a presentation and I'm going to go over fasteners. Feel free to interrupt at any time. The key point is that this is a question and answer, but I'm going to share some information in the process until we get to that point. So let me get this switched over here. All right, so we're going to start out with some fastener types. These are what you would call the self-threading types. These are a type of fastener similar to like a drywall screw or sheet metal screw. And I'm going to start out talking about the types of tips that these have. There's subtle differences, but they're extremely important. We'll start with this middle one here, which is a self-drilling. This one's obviously pretty different. You can see down here that it actually has a point that looks pretty similar to a drill bit. Now, the reason for this is it can drill through a piece of metal, so you don't need to drill a pilot hole ahead of time. And there are limits. These can only go through so thick a metal. There are some special varieties that can go thicker, but we'll talk about those in a minute. And these typically go through, well, they typically go straight into metal, or they can go through something like really thin, like a thin sheet of plastic or a thin sheet of wood, and then drill into the metal. And what they'll do is they'll actually strip out the first piece that they go into, and then they will lock into the second piece. So they'll like strip out the plastic or strip out the wood and pretty much design their own hole. And after that, then they'll anchor strongly into the metal. Next, we're going to talk about self-tapping. You can see the point on this. It's a little more, it's a somewhat blunt point. I mean, it's still a little bit sharp, but the key thing on these is you have to pre-drill a hole. And the point is really just to get it aligned and started. The point doesn't really, do anything per se. And these are, I'm trying to think of the best situation on these. These are useful if the metal is too thick to pre-drill it. Um, but ultimately, these are better into like a wood. You don't really use these into metal except for special applications. There are some self-threading metal screws that are not self-drilling. You see them a lot in automotive, and they usually have kind of a weird tip that kind of has some serrations on it. But we're not going to cover those today. That's kind of a specialty item. There are so many types of fasteners. There's millions of types. And, you know, I'm sure I've only seen a small percentage of them, but we have plenty to cover today, that's for sure. So we'll get on to the third type that we're going to look at briefly here. And this is a self-piercing. This one has a really sharp point on it. And these are made to punch through metal. You could think of these in like if you're installing drywall on the corner of a wall and you have like a really thin piece of flashing, this will just punch right through it, and then that point will go into the piece of wood. So these are pretty universal. You could also kind of use these for wood screws, but being they're a sheet metal screw, they tend to be harder and more durable and makes them very universal. Like if you took a wood screw and you tried to use it for this purpose, you'd end up just pretty much destroying it. So I'm going to switch over to my other camera here so we can, let me see here. All right, a little new at this. All right, there we go. So there's my other camera, and it's seeming to have a little trouble trying to focus on this. Let's see if I can straighten these out. I've got a new camera coming, but you're going to deal with me for today. So you can see the three types here. This one here is your self-drilling. You can see that it's got, you know, this kind of drill bit point on it. And then you can see this one here. This is the self-piercing. So this has the really sharp point. You can kind of see it there. And then this is a self-threading. This is actually kind of more of a wood screw. It's kind of a, I guess I'd call it a large wood screw. I believe this one actually will work on sheet metal, but sometimes you just have to kind of test them and see if it's too soft. If it's a wood screw and it's too soft, you'll just strip it out when you try to run it into a piece of metal. If you buy the package, it'll tell you exactly what it is, but I just had these laying around in my drawer, so I don't know what it is. Let's see here. Let's go on to the next. I'll switch this back here. There we go. All right. So these screws have a ton of different types of heads. So I'm not going to cover all of them here. They're pretty extensive. So first type we're going to have here is the flathead. The flathead is typically going into like a piece of wood where you would countersink it, and you want to get this nice and flush, and you want to hide it so nothing's sticking up. These are pretty universal. You're not really going to use them where you have a piece of sheet metal because it won't sink into it properly. So you can think of this as more of a wood type screw. Next, we'll go on to the, you have a flange head. This has kind of a washer built into it. And there's a lot of different varieties of these. You can see these called like a flange head, a waffle head, a truss head. But the key thing is it has a round load-bearing area, essentially a built-in washer that's going to distribute the load. Binding head, that's your pretty standard screw. You're going to see that all over the place. It's what's been around since the beginning of time. It's kind of good all around. It gives you a flat surface on the bottom. It's inexpensive. This one here is a flathead. Flatheads are kind of a pain in the butt. I don't use them often. They look nice for decorative work, sometimes with wood. But outside of that, I would not use them much. For some reason, the Germans seem to really like flatheads. I'm not really quite sure. But they do. Bulge head, dome head. Okay, so this dome head, this is pretty similar to the binding head, but it's a little larger in diameter. Gives a little more surface area. And then we have, okay, this here's a raised head. This is similar to the flathead, but you'll notice that it kind of has a dome coming out the top. And that allows you a little more area to get the screwdriver in there. You can get a little more torque on it. It can be a nice decorative element, if you're okay with it protruding above the surface. It's kind of more in the wood screw category. I haven't really seen these in any other application. Truss head. These are very popular. You're going to see these at Home Depot. You're going to see them all over the place. These are good for attaching corrugated metal. They use them for attaching the lath or for adding stucco to houses. Pretty much any time that you're trying to attach a thin piece of something to a thicker piece of something. Pretty much any type of thin metal to wood, this is pretty much your go-to screw unless you have a specific application. Combination head. So you'll notice that this one will accept both a flathead and a Phillips head. These are pretty handy if you're trying to make something that you need to be able to do repair work, like out in the field, and you don't know what tools you're going to have. You don't see these a lot in production. They're kind of a specialty tool or specialty screw, but they're extremely universal. Next, we're going to look at, okay, this is the pin head here. You're not going to purchase these very often because these are more like an OEM type thing. You'll see these on like your cell phone or expensive electronics that they don't want you taking them apart. You need a special Torx wrench with a little hole in the middle of it to get these apart. Sentinel head, I've never used those, so I couldn't tell you. The two-hole head, this is another type of security head like the pin head, and you don't see these a whole lot. You might see these in like bathrooms where they're like patching the walls and stuff, and they don't want people to be able to take them apart. Phillips head, this is your most common run-of-the-mill. They're pretty universal. They won't take as high a torque as like a hex head or a Torx head, but they're super quick to put in because they're kind of self-aligning. You just pretty much throw the driver bit into it and it finds its way. Internal hex. These are usually called Allen head, but that's a brand name. So internal hex, this is kind of a higher torque application. Also, you'll notice on these, heads are pretty small. They're nice as opposed to something that would have like, you know, a hex head up here on top, because you don't need to be able to get a wrench around it, which provides you a lot more room to work. However, they usually have a pretty small area underneath the head, so they're not ideal for attaching kind of soft elements that are easy to deform. So they're best for usually like metal to metal applications. External hex, like we were just talking about before, these are great. They can actually handle more torque than the internal hex. They tend to be less expensive, and it's pretty convenient to just get a socket on the top of these, but they do require a little more room than like the internal. So you do have to have enough room to work with, but they're great for when you just need to, you know, put together a lot of stuff very quickly and you need high torque. They're very forgiving. Let me see here. Posi drive. I'm not going to go too much into this, but this is the newer version of the Phillips that basically has little ridges in it to help grab onto the Phillips bit driver, and they'll take a lot more torque and they're a lot less likely to strip out. I think we're going to see a lot more of these going forward. This Quadrex head. Okay, I've never actually seen a name on these, but these will actually take a square drive and they'll take a Phillips. And you'll see these a lot in electrical because electrical work, they like to use the square drives. It's just another universal one. Instead of having a Phillips and a flat, you can have a square. I've heard them called Robinson drives also, but I just call them square drive or Phillips on the same one. Slotted head, we talked about that before. This is just a different style. It's a little beefier walls. Okay, here we go. This is our square drive. This one here appears to be a deck screw. These tend to be replaced by a Torx because these just don't have the load carrying capacity that like the newer Torx do, and we'll talk about those in a minute. So this is kind of becoming an old design that you only really see a whole lot in electrical work. So I'm going to talk about let's see, Starhead and Torx. I honestly don't know what the difference between a Starhead and a Torx is. So I'm just not even going to bother with the Starhead. Torx, those are tending to replace Phillips, and especially the hex drives, the internal hex. They take a lot of load, and you can just drive these in. They're extremely forgiving. They're also really nice because you tend to be able to reuse the screws a lot of times because they very rarely strip out. So we're going to go back to this since we talked about Torx. This is a Torx Plus, which we're going to cover a little later. It's a newer version of the Torx that can handle more torque. But more on that later, like I said. Okay, specific designed heads. These are kind of industry specific. We already talked about the flathead. This tends to be like your deck screw. Also, drywall screws have this type of head, but they tend to have a thinner shaft and they have really sharp teeth on it. They want to be able to punch through. They don't need to have quite the holding power that a deck screw does. Let's see here. Panhead screw. Yeah, don't use those a whole lot. Okay, these trim head screws. This one here is a Torx. These also come in square drive or Allen head, the hex head. These tend to have a very small head, allowing them to sink into the piece of wood. You can think of them a lot like a finishing nail that has like a really small head on it, but this is kind of a newer version, which is going to give you a lot more pull into the piece of wood underneath the trim, as opposed to like a nail. And as we talked about, the washer head or truss head, or whatever the fancy name of the day is. Wafer head is another similar one. It's got a little different shape, but once again, it's the larger distributing washer. And those are good. Like it says, softer materials, and that's especially like if you're attaching like a piece of softwood to a metal frame, or a piece of softwood to like a 2x4, or even like a rigid foam or some flexible plastic. Let's see here. Okay, these are an interesting screw. These have little wings on them, and I personally have not used these a whole lot. So they have these little wings. You can see them here and here. And these are specifically for attaching wood to a metal frame. And what they do is you drill, typically when you drill through a piece of wood, and then you drill into a piece of metal. So let's see, we have a piece of wood here. Whoops, that's not very straight. Okay, let's undo that. Okay. So you have a piece of wood, and then you have a piece of metal. And you run your screw through here, and then you hit the piece of metal, and then you drill your hole through a piece of metal. The problem is the threads have already worked their way through the piece of wood. So when you run down onto the piece, when this head here hits the piece of wood, it's going to stop, even if you haven't gone through this piece of metal yet. And so either you're not going to go through the piece of metal at all, or you're going to have a gap between the piece of wood and the piece of metal. So you might just have the screw through a little bit here through the piece of metal, and then this big gap. So what these little wings do is they actually work as a drill to go through the wood. So as they go through, they drill a hole through the piece of wood, and they actually make a hole that's larger than the screw itself. So when the screw tries to go through, it'll be nice and loose. But then after it drills through the piece of metal, it'll actually break off these little wings, and they'll just snap off. And that allows you to pull the piece of wood nice and flush up against the piece of metal. And I haven't used these a whole lot, but I'm definitely going to have to look at them more because it's a very clever design. Next, we're going to get into, these are a thick metal drilling, self-drilling screw. And you'll notice on here, put that on, you'll notice that the distance of the drill part is actually really long. And the reason is if this is short and your metal is actually thicker, you'll actually hit the first threads before you make it through the metal. And what's going to happen is then the threads are trying to push this screw through the metal before it's finished drilling the hole, and you're just going to snap the screw in half. There's basically no way that it's going to work unless the metal's just so thin. But at that point, you're not running into this problem. So the way they solve this is they put a much longer drill section on it to allow you to get through a thicker piece of metal before you actually hit the screws. And there are limits on this, and you really need to get a screw that's specific to the thickness of metal that you're working with. And the reason is that trying to get through a thick piece of metal like this puts a lot of load on that screw, because this screw is actually, tapping its way in just like a tap. And for anyone who's ever worked with taps, if you're not real careful with them, they're pretty easy to break. So what you need to do is, the thicker this metal is, the larger, let's see here. The thicker the metal is, the larger the diameter of this drill area needs to be. Because if you have thicker metal, you actually need less thread engagement. So let's see if I can explain this a little better. So say this is your hole, and your threads are going to be self-tapping. And you can see here how this is actually cut away just like a tap. This first half of the screw is essentially a tap. So when it threads in, it's going to be cutting in like this. And it's going to be making its own threads, and that's what's going to give it a lot of strength. Now, if you have a thin piece of metal, let's see here, thin piece of metal, you may only have one thread that's actually digging in, or if it's really thin, you're not going to have any threads. Your threads are actually going to be on both sides of it. That's what you're going to have with like a flashing. This is definitely not, a high strength application. This is for like, doing drywall and stuff like that, or adding sheet metal flashing to things. When you're dealing with a thick piece of metal, like we have over here, you're not going to need quite as much thread engagement because you have multiple threads catching. And if you had a really deep thread engagement, you'd get one thread, you get two threads, and by the time you get the third thread, you'd probably snap the head of the bolt right off. So the more thread engagement you have, the more thread you have actually engaging into the larger piece of metal, the less depth you need of that thread. So you need to be really specific on what screw you're using for what application. And I know I'm getting a little long-winded on this, and I can cover it more in the future, but my main point here is when you start getting into specialty fasteners like this, you really need to know what you're working with. It opens up a lot of opportunities. The ability to not have to pre-drill holes is a huge time saver and a huge money saver. And especially if we're trying to bring some manufacturing back to the US, we really need to know what technology is available to us, because we don't have the labor to do things the way we used to. But luckily, a lot of this technology that's been developed over the last few decades is going to provide us a lot of options. And I'm still learning too. There's new stuff coming out every day. So let's see. Go to the next one. Okay, so I was mentioning earlier that Torx bolts tend to replace a lot of the Phillips or the hex head. So we're just going to look at this a little bit. This is an interesting diagram. I think I just want to show this lower part here. So this is showing how you have a lot more engagement. You have a lot more engagement as far as surface area goes on the Torx threads. With the hex head, you can actually turn the bit quite a bit further before it actually locks down. And anyone who's ever, rounded off a hex head bolt, it's the same thing, but just internal, and you have even less to work with. But just the amount of surface area you have on the Torx, it's almost impossible to strip these out. You'll usually end up either breaking the bolt or, actually breaking the Torx driver, before you strip these things out. Let's see here. Yeah, just showing it further. So that's all I really wanted to say about that. I just think Torx are going to kind of really become the standard. They've already replaced so much, and they're just going to continue to do so. Next, I'm going to get into sealing screws. These are screws that have a little rubber washer built into them. And if you've never used these before, these are used for like sealing applications where you're trying to attach a piece of sheet metal and you want it waterproof. These are primarily used for attaching corrugated metal as a roofing material. I've even used these to repair a hole in a gas tank. Anytime you're trying to keep water or air or any type of gases out, they're a quick and easy way to go about it. They're not anything high tech, they're pretty low tech product, but they just do the job, and they're very inexpensive. There is a little bit to keep in mind when you're using these. You really need to keep the torque proper on these. You can see here. If you don't run these things in far enough, you end up with a gap. And what happens is when it rains, the water just comes in, comes underneath, comes in here, and ends up rotting your wood. And it can actually even eventually run all the way down the screw and drip into your building. And then you have damage. But equally, or almost as important, you don't want to overdrive these things either, because you'll actually squish them out. They'll actually extrude. And you'll usually get an all right seal for a while, but because you're pushing so hard on it, you'll actually squish it out, and you could actually split the washer. And over the next year or two, you're going to run into a problem. You probably won't notice it right away. So this is how it should be, where the washer should be snug against it. You want to compress it, I'll say 10 to 30% of its thickness. You'll get the idea. Basically, when you run it down, you should notice it expand just a tiny bit. If you see it squishing out a lot, you've done it too much. If you don't see the washer expand any, then you probably don't have enough torque. It's pretty easy to just, set the torque driver on your drill once you've got it dialed in, and then you don't have to worry about it. But as I talked about before, you have the opposite problem where I was talking about how you could run through the piece of wood. And let's just do this opposite here. Like if you were running through this piece of wood and then all the threads are digging in, and then you hit this piece of metal, you won't drill all the way through it because the head's going to bottom out here before you get all the way through. So you have kind of the different situation here. And these self-piercing points, they really only work for really thin metal, because you're actually going to drill through this piece of metal, and then you're going to hit the piece of wood, and you're going to drill in. And when this head of the screw actually hits the piece of metal, it has to actually strip out this piece of metal in order to drive it all the way down to the wood solid. If this metal is too thick, like if we had it thicker and you ran this screw through here, you run into here, you'd start pulling this down, but then the screw would stop, and the screw would stop turning regardless of how far you went into the wood, and you'd end up with a gap between the metal and the wood. So you definitely need to only use these screws in thin sheet metal applications. Let's go on to the next one. Okay, I was mentioning before the difference between Torx and Torx Plus. And they're fairly similar. I first started working with these when I was working for General Motors about a while ago, well over a decade ago. And we were moving on to this Torx Plus design, and they take more torque. Like these regular Torx, you kind of have a weak spot up here where this is kind of trying to push through because it's kind of small. With the Torx Plus, you have a larger bearing area here, and you still have just as much, you know, area to take the force as you do, because on the regular Torx, you don't actually do a whole lot way up in this point here. Most of the load is applied, in this area. So by rounding off the corners, you don't actually hurt anything, but you just provide an overall more solid joint. And I haven't seen these take off a whole lot, but you can actually use a regular Torx driver in a Torx Plus, so it's not a big deal. If you do switch to the Torx Plus, it's not going to be a problem as far as maintenance. However, the regular Torx driver will not handle as much torque as the Torx Plus will. So you are, sacrificing a little bit of the durability if you don't use the proper tool. Let's go on next here. All right. So this is a specially screwed. This is for attaching foam panels to walls. So it's just a normal wood screw. But then it has this plastic washer on it, and they're large diameter, usually like 2 inches in diameter. And this allows you to actually screw a piece of foam onto a wall and not have the screw pull through. And there's, thousands of specialized applications. This is just one that you'll come across, excuse me. And you'll commonly find these at like Lowe's or Home Depot. It's definitely a construction project type of application. Next, I want to talk about lag bolts. These are basically just really big screws. I would say anything like a 1/4 inch or larger, you're going to start calling it a lag bolt, as opposed to something smaller than that, you would call it a screw, construction screw, drywall screw. Lag bolts typically have hex heads, so you can drive them with a socket and you can put a lot of torque on them. Typically, these are used for driving one piece of wood to another, like you'll have a 2x4. Oops. And you're going to drive that into another 2x4. And it's going to pull this gap shut. You use these a lot for building decks and any type of like wood construction application. To use these, you have to pre-drill the holes. Otherwise, you're just going to split the wood. So let's say this is our top piece of wood, and this is our bottom piece of wood. So you're going to drill a larger hole through here, and then a smaller hole into the bottom piece. And this larger hole here, that's going to allow this unthreaded part to fit in there loosely, because you don't want that to be tight. You want that to be loose. And then this bottom hole, that's going to be an interference fit that these threads can cut into. And then that's what's going to pull it all together. And when you use these, you definitely need to use a washer on here, because you're going into a piece of wood. So you will, you'll pull through and damage your entire project if you don't use a washer with these. So washer, hex head, and bolt comes through. Okay, let's see what we have next. Lag bolts, or lag eye bolts. This is a specialty application. Let's see here. I'm sure you've all come across these. Oops. This is your most common. This is what you get at Home Depot. It's just a piece of bent wire, and it tends to be open on the end here. These are definitely not for load-bearing applications. These are good for, you could use them for like tying up a boat or something, but you don't want to use something where if it fails, you injure the person. I have welded these shut here, and it does make them a bit stronger, but you do have to keep in mind, then you're just moving your failure point to these threads just ripping out of the piece of wood. So you have to keep in mind, it does improve it, but it doesn't make it load bearing by any means. Then we get into something like a forged eye bolt. And some of these actually have a load rating application. And you have to have the right wood. And if you really want to be load bearing, you really need to have an engineer spec out this type of wood and this type of application. This is your thread engagement. But keep in mind, when you are getting into a product like this, you are getting into something that has a safety factor built into it. So there are a lot more applications. We have these lag screws. It's similar. It's just for a much tighter confined area. Let's see what else we have on here. Let me grease all these. All right. So this is something that you'd see like, for tying up horses or anytime you're working with rope. It's kind of a specialty application. These eye lag screws, these are really handy because they're super tight space. They're very easy to drive in. For most of these, you just stick a screwdriver in there and run it in. They also do make special tools that you can run these in with power drill. And these are nice. They're inexpensive, but the availability of them isn't huge. You're starting to see them more often, but at Home Depot and Lowe's, I have not seen them a whole lot. You may have to get them from like McMaster-Carr somewhere. This is the type of deck screw we're starting to see more of. These are kind of a specialty application. If you think of normal deck screw, it would not have these. This. It would not have these threads at the top. And what these threads do is as you're running in a piece of wood, they actually tighten into the top piece of wood and not just the bottom piece of wood. And they actually drive the two pieces of wood together. So instead of just having the top piece loose and the bottom piece doing all the work, this is actually going to be a much tighter bond. And you'll also notice here, this is in a sense a self-drilling screw, but it's a self-drilling screw for wood. I have actually driven these through thin sheet metal. You can do it. It's not their application, but it does work in a pinch. But what this does is this little cutter here, it helps push the sawdust out of the way and helps keep from splitting the wood. We're starting to see a lot more of these little features incorporated into purpose-built fasteners, which is actually making construction and manufacturing a lot easier for everyone. And sometimes it's just little things that can solve a ton of huge problems. So that's all I'm going to talk about self-threading screws for right now. If you have an interest in knowing more about any specific topic, just let me know in the Q&A and we'll discuss it more. And I'm not limiting the Q&A to just fasteners. That just happens to be some stuff I'm presenting today. So if you have any other related engineering questions or even related to like construction or automotive, drop them in the chat and see what we can do. We'll cover whatever you're interested in. So I'm going to go on to let's see here. I'm going to talk about a bit about bolts. So a bolt being a little different than the self-drilling screws that I talked about before. Now, it's a little confusing because people like to talk about bolts and they talk about screws. And technically, a bolt and screw is the same thing, except typically we call it a bolt if it's a 1/4 inch or larger, and we call it a screw if it's smaller than that. I can't say the exact cutoff for metric. Metric, I guess I would personally say, somewhere around 6 millimeter. We're going to switch the terminology from screw to bolt, but it's essentially just two different descriptions for the same thing. The key thing that we really want to differentiate here is before we were looking at like a self-threading screw that has, a pretty steep thread. It's got sharp threads that are going to drill as it goes in. So what we're looking at here with these bolts is these have to be pre-tapped. You either have to have a hole that you've tapped the threads in ahead of time, or you have to put a nut on the end of it. These are not going to cut their own threads. I mean, if you try to run into a piece of plastic or something, yeah, it'll cut some threads, but these just aren't ideal. Plastic, you'd be better off with something that's self-threading like we talked about before. So that's our big differentiating factor here, is that we're dealing with something that requires a pre-threaded nut or casting or, block of steel or something otherwise. Okay. So first thing I want to talk about is you have fine thread and you have coarse thread. And the coarse thread is definitely the most common. It's, if you just go to the hardware store, you pick up a bolt, about 90% of the time it's going to be a coarse thread. These are great for general projects. The coarse threads tend to be more forgiving if they get dirt in them. They don't strip out as easily. They're just overall easier to use. And on the other side, we have a fine thread. So the threads are much closer together. So these will actually clamp tighter. And the reason for that is, let's say we put a nut on here. And in that nut, we're getting 1, 2. I mean, we're really getting 2 solid threads of engagement, maybe 2.5. When we go over to a fine thread, we're getting 1, 2, 3, possibly 3.5 to 4 threads. And even though the threads are smaller, they will actually add up to being more clamping force. And that's why you see these a lot in precision applications. Aerospace is almost all fine thread because they need all the strength they can get in whatever weight of, bolt that they're required to use. And we'll talk about that a little more. But there's certain applications that you really need to use a coarse thread. Like, say you have an aluminum casting. Usually castings don't hold the fine threads all that well, and you're more likely to strip them out. You're actually better off with like a coarse thread. Even if you get fewer threads engagement, you're going to be less likely to just rip the threads right out of the casting. So I'd say most of the work I do is just with coarse threads. They're inexpensive and they're good enough for 90% of the work. And I guess one thing you'll notice, like engine bolts, they go into castings. They're always coarse thread. And I'm trying to think of fine thread when you always use a fine thread. Lug nuts, they're always fine thread because you get more holding power with them. And also, being that they're a finer thread, try to think how to best explain this. But because they're flatter and they don't have as much tilt, they don't try to come undone as much. They're much less likely to work out. A coarse thread is far more common for them to come loose on their own than a fine thread. So, as in the case of lug nuts, obviously you do not want those coming loose. Okay. All right. So we're going to take a look at some standard thread sizes. This is a comparison of coarse thread and fine thread. So you can see with this first one, we have a 1/4-20 and we have a 1/4-28. So the 1/4 inch is the diameter of the bolt. So that means this diameter is the same as this diameter. Now, both of these bolts, as far as the shaft, is going to be the same strength, assuming that they are the same grade of bolt. But we're going to talk about that more in a minute. However, as you can see, as we talked before, you have a lot coarser threads there and, super fine threads here. And you can get coarse and fine thread in every size. So you can see 1/4 inch, 5/8, 3/8. And you can see these are being called out as bolts. And like I was saying, that's kind of 1/4 inch and up. Now, these fine thread and coarse thread exist in smaller pitches also. But when you get below 1/4 inch, it goes into number sizes, or I guess you could call it a gauge size, but it's really just a number size. Below a 1/4 inch, you have a size 12, which is very uncommon. Then you go to a 10, 8, 6, 4. And then after 4, it goes to 3, 2, 1, 0. And then you even have double zero, like incredibly tiny. So that's how you can tell apart screws and bolts for U.S. standard, is if it's a number size, it's a screw, and if it's called out by the diameter as a fraction, it's a bolt. Metric doesn't really work that way, but we'll talk about that in a minute. Now since we're still on the U.S. standard SAE style bolts, I want to talk a little bit about the grades of bolts. Now, this here, let me zoom out of that just a hair. Okay, this starts out at grade 2. Now, grade 2 is going to be your low-grade bolt. This is what you would use for putting together a wheelbarrow, lawn furniture, other non-critical applications. Now, what they don't have here that I think should be called out, there's actually something, I would call it a grade 1, and they're usually marked, whoops, let's get rid of that, 307A. And that's even a lower grade. Basically think of it as ground up coat hangers and rebar. So when you watch those videos on YouTube where, you got the factory in India that's straightening out the old piece of rebar and, making screws out of it, you're probably dealing with something that's like a 307A. The grade 2 can actually be as low quality as a 307A. There's not a lot of regulation. The grade 2 does not have any marking on top. So I would just assume any grade 2 is as weak. Any grade 2 here is as weak as the 307A. They're both very low quality bolts. And this isn't necessarily a problem. You have a lot of applications where this is the absolute cheapest way to build something. Because, well, it's a very low-grade steel. Steel is still very strong. Even if you're talking a low-grade steel, it's still 30,000 PSI of strength. The downfall with these is they tend to be, heavy for their strength. And anytime that you need something where weight is a consideration, then you want to avoid like the 307A or, the grade 2. And also the quality control is not going to be very good on them. So I would never use one in like an automotive application or, anything where human life could be in danger if it's failed. So next I want to get on to the grade 5. So these grade 5 have the 3 lines on it. And these are extremely common. They're often called an automotive grade. And, that just goes back to a long time ago. Once the automotive industry got going, this was kind of the standard they used for everything. These are common in cars. You'll see them a lot in sometimes like chassis components and, holding fenders on and stuff like that. But a lot of that's being upgraded to grade 8 anymore. The thing to keep in mind on these grade 5s, these are extremely counterfeited. So if you're getting these out of, say, China or, anywhere overseas that you're not, aware of the quality coming out of the factory, it's not a name brand, you could actually be getting like a grade 2 bolt that they just stamp 3 lines on the top of it. So if you need the strength, make sure that you are getting it from a reputable supplier. Grade 6, I can honestly say I have never seen a grade 6 bolt. And then we get into grade 7. I have never seen a grade 7 bolt ever anywhere. And then we get over to grade 8. And I believe the reason that we don't see grade 6 or grade 7 anymore is, if I was to guess, I would say that we had the grade 5s and then they needed something stronger, so they came out with the grade 6, and then they needed something stronger, so they came out with the grade 7. But then when they finally came out with the grade 8, they just kind of discontinued the grade 6 and 7. So really, we're dealing with just the 307A, the grade 2, the grade 5, and the grade 8. grade 8.2, I have never seen those. I've heard of stuff like grade 9 or grade 12. There's some question on whether that's more of a marketing gimmick. I haven't really dug into it to see what the standard would be for a grade 9 or a grade 12. But I will just say those do exist out there. So if you do need something that requires something stronger than a grade 8, there are some applications available. The grade 8, this is starting to become more of like the automotive standard. Anything that's like a head bolt on an engine or anything that requires, a high torque is going to use the grade 8. And the nice thing is a lot of time you can get away with a little smaller bolt going with the grade 8 than a grade 5. And the savings in weight is often, more than worth it. A one size smaller grade 8 bolt might be cheaper than a one size larger grade 5, and it may be just as strong. Then we're getting into metric here. So the metric have a number on the top of them, and that's the easiest way to tell the difference between a metric and a US standard bolt. So the 5 is the strength of the bolt. And don't quote me on this, but I believe that is the tensile strength in megapascals for the steel. And once again, everything I'm talking about right now is for steel bolts, not for stainless, not for brass, not for aluminum. This is purely steel bolts where the standard applies. And then your 8 is the yield strength of the bolt in relation to the ultimate strength of the bolt. So let's just say, for the math, make it easier, we'll look at this grade 9, or 10.9. So you're talking about an ultimate strength of 10 megapascals, I believe, before it breaks. But at 9 megapascals is where you're going to start having a yield, and that's when the bolt starts actually stretching to the point that it deforms and doesn't go back. So you can think of this 8. Sorry, that's not working. This 8 means that the yield strength is 80% of the ultimate strength, and this 9 means that the yield strength is 90% of the yield strength. And as you start getting into these stronger bolts, the 10s and the 9s, this higher number for the yield strength automatically comes along with it. And the reason for that is that as steel becomes stronger, it also becomes harder and becomes less flexible. So what happens is your yield point, or the point at which the metal deforms, gets closer and closer to the ultimate breaking strength. If you think of like a really low grade bolt that's made of, soft metal, like a coat hanger, you can bend that all over, you can stretch it, you can deform it a lot before it breaks. And that can be kind of handy if you're in an application where, some damage is allowed, but you don't want it to snap off. But when you get up into the stronger stuff, you have to really be careful on how you build, because you get to the point you start bending that bolt, you're basically just below the point necessary to snap it in half. Okay, so we're going to look at the metric here. Let's zoom in a little. Okay. So going by what Bolt Depot has here, they're calling an M4 a bolt. So we'll just go with that. We'll say M4 and larger as a bolt, and M3.5 and smaller as a screw. So that works for me. I don't know that there's an actual standard, but that works. So just like the US standard, you're dealing with the same thing. Your 6 millimeter is pretty similar to your 1/4 inch. Your 8 millimeter is pretty similar to your 5/16. Your 10 millimeter is close to your 3/8, and then your 12 is getting close to 1/2 inch. Not exact, but they're getting in the same ballpark, and they're going to have similar strength, assuming they're of the same standard. So being that the US standard is grade 5, grade 8, and the metric standard is going to be like a something point something, They're not an exact match, but you can cross-reference them on a chart and get something that's going to be comparable. Do keep in mind that the diameters are slightly different. So you can't just take a half inch and replace it with a 12 millimeter and expect it to work the same. The half inch, it's probably going to be a little stronger and it's going to fit the hole properly because it's a little thicker than the 12, because half inch is actually 12.7 millimeters. So unfortunately, in America, we have to deal with both standards on a pretty regular basis. And maybe I'll get into that a little more later as to, why we haven't fully converted over to metric. There are reasons for it. We have converted over to metric a lot more than most people think. All our cars are metric. Our airplanes are all now metric. A lot of the machinery is metric, but machinery is a little slower. And construction, most of it is not metric yet. And that all has to do with like legacy. We replace cars all the time. Cars are a self-contained unit. It's easy to convert that all to metric. Machinery is a little tougher. Machinery can stay in a factory for, 50 years. And there's a lot of tooling and stuff that has to be backwards compatible. So it's a little harder to convert it. And then when we get into construction, we have infrastructure that is 100 years old that we need to replace piecemeal. And you're not necessarily replacing the whole thing, which makes it very different to convert it all over to metric. So I do not foresee metric completely replacing all US standard fasteners at any type in the near future. I still use a lot of US standard, more so than metric, partly because it's just really more available as far as, just all the different specialty stuff. It just kind of ties into the whole ecosystem that we've been using for, well over 100 years. Yeah, I do wish it all was metric, but yeah, it's not a flip a switch type of thing. Okay, next, Next, I want to talk about, what I got there, no. I'm going to go back to, okay, well, I'll just talk about it real quick. I thought I had another slide here, but these are set screws. They typically have a no head. They just have a hex drive on the inside. And the reason is because these are typically used in rotating shafts. And when something's rotating, you don't want a big screw sticking out the top like this to be spinning in circles. And there's two reasons for that. Well, there's multiple reasons. One, that'd be a safety hazard to have this thing spinning around that could, take off a finger. Another thing is sometimes you have clearance. Sometimes you may have a wall right here to the piece of machinery, and that thing comes around and it hits it. And also, when you get into higher speed applications, having a bolt stick out the top could actually run into a huge vibration problem, and you can actually shake the machine apart or destroy the bearings or something like that. But yeah, you're usually dealing with a hex head on these. I don't know why they haven't really converted these over to Torx. I think we'll probably see that more in the future. But you have your Allen hex head on these. Sometimes you'll see like stainless steel set screws, and I try to avoid these when all possible because they tend to strip out really bad. And if you get a hex head or you get a set screw that's kind of stuck, like I was designing some equipment that was processing cannabis equipment, and you get the resin down in the screws, and we just couldn't get them apart. And I had to do away with all of the stainless steel screws, and I had to actually go to something that had a yellow zinc coating, which is just a really corrosion resistant, but still had the base screw as steel, which was much stronger, and it got rid of my stripping out problem. And there's so many other things to talk about with that, with like galvanic corrosion and other issues that come into every design. So I think I'll definitely get into a lot more design elements going forward. I wanted to kind of start out with something kind of basic today, and I'm really looking for like any type of input that you might have on what you really want to see. I really do want to focus on like the design aspect and the manufacturing, but its entire ecosystem, because oftentimes I will use fasteners that are designed for construction in the manufacture of a product or vice versa. And that is really nice because construction parts tend to be very inexpensive. So anytime you can use like a mass market part in a smaller market product, you can save a lot of money. And construction materials tend to be really well made as long as you buy something that's spec'd for your application. Let's see here. Next. Okay. Thumb screws or wing screws or whatever you want to call them. These are something where you need to be able to, remove the screw without using any tools. Probably one of your most common and least expensive is like this thumb screw here. And these are great for holding on like panels, access panels, or, anything that you need to be able to get to on a regular basis. It's not something that you want to be able to open a hatch every day because obviously taking out screws is going to be a pain in the butt. But if it's something you need to get to once a month or once a year, and you may not have any tools on you, it's a great option. This is a little different option. You can see that the thumb part is smaller. Not something I'm super fond of, but these will fit in tight spaces. Also, this has a washer on the bottom, which is going to allow for something to clamp tightly. This design here is actually not overly useful in general because it doesn't really have a head to, lock down on anything. So you can use these in like a pinch, but they're not great. This is another application here. This is actually just a standard screw. This is usually like just a hex head. So you usually just have a round head bolt in here. And then you have this piece of plastic, which is just a press fit, and you push it on there. And these are nice for low torque applications. If you try to torque them down too tight, you will actually strip out the plastic where it interfaces between the metal bolts. But a lot of hex head bolts, they have little lines on them like this on the outside of them, and those help it dig into this plastic. So if you have like a really smooth hex head bolt without the little lines on it, they're not going to hold as well. This one here is something similar. I'm guessing from the look of this is actually over molded. So they'll actually take a regular bolt of some type, they'll put it in a molding machine, and then they'll mold the plastic over it. These tend to have a little more holding power. They don't break out as easily, but it really depends what they use for the base bolt here. I mean, if it's a really smooth one, you could still break it out. Anyhow, there's hundreds or even thousands of types of these thumb bolts or, knobs. You just have to find some that's appropriate for your application. Some of them have more plastic, some have more metal. Some are all metal with like big round knurled tops on them. Let's see here. These are carriage bolts. They go back to the original terminology when people made carriages with them. And they basically go into a piece of wood. And when they go into the piece of wood, it keeps them from spinning. So you drill a hole. Oops. Still getting the hang of this tablet. So you drill a hole just large enough for the bolt to go through, but not large enough for this square drive to go through. Then you take a hammer, you pound it in, and what it does is it locks it into this piece of wood. So you have a large square hole, and then you have a smaller hole here. And then when you put the nut on it, it keeps the bolt from spinning in the piece of wood. So it locks it in place. These are usually a pretty low grade. They're usually like a grade 2. However, you can get grade 5 and grade 8. A newer application, I don't want to say newer, but another application that's newer than the original carriages is instead of a piece of wood, you actually have a piece of steel that has a square hole punched into it. And the bolt will drop into this square punched hole, and that'll hold it in place in the same way as knocking it into a piece of wood. Another similar bolt you'll come across, this is it's called an elevator bolt. And it's similar to a carriage bolt, except the top of it is flat. And this is I believe that the name actually comes from, they use them in the floor of elevators or possibly in the walls also. So you have a floor of an elevator and you have the bolt and it sinks in like that, and you put the nut on the back. So it allows you to have a completely flush top. These are not as common, but they're very handy in some applications. Next, this is what's called a plow bolt. It looks kind of similar to the carriage bolt, but it just has a slightly domed top, not as much as the carriage bolt, but not as flat as the elevator bolt. But what you'll notice that's really different on these is the underside has this taper. And as the name implies, these go into a plow that's used to plow the field. And these bolts tend to be very high grade. You're talking like grade 8 or stronger type of bolt, because they need to be able to, pull rocks out of the ground and, do any type of, heavy duty applications that you might run across. Next, I want to look at, this is a threaded rod, also known as all thread. It's essentially just a bolt without a head. You can get these anywhere from, really tiny, like 1/2 inch long, up to, a 12-foot long rod. You see these in a lot of construction applications where they're trying to hang things from ceilings. They also work in machinery or other applications where they just don't make a bolt that's long enough. Instead of using a bolt with a nut, you would just put a nut on both ends to make your own custom length bolt. And these are available in all grades. Most of them are low grade, but they do make higher grade versions of them. This is what's called an Acme thread. You'll notice it's kind of similar to the all thread that I showed in the previous slide. However, you'll notice that the threads on this are actually really square. Now, these have a completely different application. These are not made for clamping things together like a regular bolt. These are actually what's called a lead screw, and they're made for motion. You'll see them in like a lathe or a mill or a piece of equipment that you need to be able to move back and forth. A lot of these in like newer CNC equipment are getting replaced with like ball screws and other type of lower friction applications. However, these are ideal for manual machines, because if you put a ball screw in a manual machine, the table just float all over the place because you don't have a motor holding it in place. So we still have a lot of applications for these manual lead screws. You can see an application right here where, let's see, we can see this lead screw right here. That's not drawn. Okay, I guess it doesn't want to draw on this one. But anyhow, you can see the lead screw here. Next, I want to talk a little bit about aerospace bolts. These are very specialized. You're not going to find these at a hardware store. There's actually very few places you could find these. Even somewhere like McMaster Car doesn't tend to carry these, except for a very small selection. If you're going to get these, you're going to probably find them surplus on eBay, or you're going to be buying them from an aerospace place. And there's several features of these that make them a bit different. I usually see a marking on the bottom of them that will say like AN, and that stands for Army Navy. Or sometimes you'll see NAS, which is National Aeronautical Standard. And these are very non-universal bolts. They're very specific in their applications. They actually sell them in very different increments. Like you'll get one that's 1 inch, and you'll get it like, 1 1/16 of an inch and 1 1/8 of an inch. And now it's going metric, but same type of concept. You just have a ton of different applications, but these are also extremely expensive, and they're not necessarily stronger than like a grade 8 bolt. In fact, I think they usually fall somewhere in between like, a grade 5 and a grade 8. And the key thing about these bolts is not so much that they're stronger than anything else. It's that they don't shear off in failure, and they tend to bend before they break. And the other thing that's very interesting about them is if you look along the length of them, a wonderful drawing today, you tend to have a very small amount of thread. And the reason for that is if they're trying to clamp two pieces of something together, you don't want to have any thread in here. And the reason is because the threads are going to start digging into this material, which is going to make a weak point. And you don't want a weak point on an airplane. Airplanes are built very close to, the strengths they need to see, because, this thing has to float in the air. So you're going to purchase, you're going to purchase bolts that are almost like the exact length of what you need just to fit a nut on here and have a couple threads coming out the end. Typically, we like to see 3 threads coming out the end of a nut for maximum strength. It's a good ballpark. I'm sure in aerospace, they can tell you exactly how many you need, 2.5 threads or whatever. That's about all I'm going to say about these right now, just that you may come across them, but they are very specialized for the application. Non-metallic fasteners. These are usually the most common, I guess, would be nylon. You also run across some fiberglass, and there's also PEEK is starting to come out, PEEK. It's a very expensive, high temperature engineering plastic, probably well over $100 a pound, and that's only going to be used in very specialized applications. You would use these in places where you need something that's extremely corrosion resistant, and usually something that needs to be electrically non-conductive. And once again, feel free to ask any questions. If I don't get any questions, I'm just going to continue to go through some fasteners. So now we get into fastener finishes or fastener coatings. There are a lot of different applications that need different coatings. We start out with the most basic, and that's going to be your uncoated. And I'm just going to be specific. Say this is for steel fasteners. We have other coatings for other types, but I'm just going to talk about steel for right now. Your uncoated is just a plain bolt. It's just a piece of steel. You'll probably receive it with a little bit of oil on it so it doesn't rust. And I use these a lot if I need to weld onto something, but they are not really an application that you would want to use for anything that has to be outside or has to be rust resistant. Next we have, let's see here. We have I'm going to lump these together for right now. We have the black oxide. You have the thermal and you have the chemical. The chemical is a very inexpensive. I believe it's just like a phosphorus coating. You can actually take like the plain uncoated, and you can put it in some phosphoric acid, and you'll get a black coating on it. And it provides you a little bit of resistance. Still not something I would use outdoors. However, when you get into like the thermal black oxide, that's when you start seeing it used in like bolts on chassis on cars and stuff. And they do rust. If you look under an old car, especially like if you're back east or in the Midwest, it's going to be pretty rusted. And that's because this thermal black oxide coating provides some protection, but not a ton. But yeah, the chemical black oxide is very minimal. It's good for like if you're working in a shop and you just need, a little bit of rust resistance. And on that note, the reason things don't tend to rust in a shop, aside from not being rained on, is you tend to get a super thin film of oil on top of everything that protects it. So anytime you drill a hole in a piece of metal and use some cutting oil, that becomes aerosolized, which is why it's good to wear a mask, but that's eventually going to float around and it's going to sit on everything and it's going to prevent rusting. Let's see here. not swelling. Oh, I gotta turn off this. Okay. Chemical black oxide, gray phosphorus. So I'm not gonna talk about the gray phosphorus. Okay. Okay, so next I'm going to talk about the zinc electroplated. This is your most common. You're going to see this on everything. You go to Home Depot, and especially if you see like a shiny surface on a bolt, it's almost always just like a zinc plating, and it's an electroplating process where you put some zinc in there, you electrify it, and through a chemical process, you put this nice shiny coating. It's a fairly inexpensive. It's a fairly rust resistant. It's kind of your go-to for everything. Because of the galvanic corrosion, the electrical difference between the zinc and the steel, the zinc is actually sacrificial, and it will degrade, protecting the steel. It's kind of similar to how you'll have like a magnesium rod inside a water heater, where the magnesium rod heats apart before it disintegrates the water heater. But in this case, the protective coating's on the outside, and in many applications, this could last for years or decades outside. But if it's subjected to a lot of salt, or it's sitting in water over time, then it will eat through it. Like, this wouldn't be appropriate for a swimming pool, and especially with the chlorine, which is just even going to speed it up more. Then we have the yellow electroplated. It's the yellow. I call it a yellow zinc. They call it a yellow chromated here. This has 2 to 3 times the corrosion resistance. This is actually what I've used to replace a lot of stainless in applications where the stainless just was too soft, because stainless bolts really aren't very strong. They're very corrosion resistant, but they're just soft and mushy, and they tend to gall and lock together, and you try to take them apart and you end up snapping off the bolt. So if you can get away with just like a yellow zinc, I highly recommend going that route as opposed to stainless if you can. The blue chromated. These are actually kind of cool. You can't really tell in this picture here, but these are actually kind of a bluish color, and they're very corrosion resistant. It's not super common. You're not going to run down to Home Depot and buy these. McMaster-Carr will have them in certain sizes. A very good, high corrosion resistant application, and you can get it in a very high, like grade 8 bolt or similar. Mechanical zinc. I'm not going to get into this one. I'm not super knowledgeable. Actually, I'm just going to read what it says here. Okay, let's see. A process by which the fastener is tumbled in a drum with glass beads, water, chemical, and zinc powder. The collision creates a cold welding of the zinc powder onto the parts. Advantages: elimination of hydrogen embrittlement, excellent adhesion, uniformity of coating thickness, and ability to plate hardened parts without post-baking. Okay, so yeah, that's actually, I have used these before, but I wasn't sure how the process actually worked. So yeah, we bounce them around in zinc powder until it forms a coating on it. Zinc is actually really really soft. It's really malleable, so you could actually push it together. Think like Play-Doh. We're gonna put a layer of zinc Play-Doh on the top of it. Probably a little better than that. But anyhow, then that gets us into hot dipped galvanized, and this is what you're gonna see for outdoor hardware. And like at Home Depot, when you see the bolts that they have a really dull, almost like flaky surface, it's not the nice shiny zinc. This is your hot dipped galvanized, where they actually take the bolts and they dip them in molten zinc and pull them out, and it puts a really nice thick layer of zinc on them. And that's extremely corrosion resistant, and it's inexpensive. It's not the most decorative by any means, but as far as outdoor applications to handle the weather, it's about as good as you're going to get. Then we have cadmium. You're not seeing a lot of cadmium anymore. Cadmium's a pretty toxic metal, and you used to see this a lot in aerospace, and I believe they still use it in aerospace a bit. However, just because of its toxicity, it is being replaced a lot by the yellow zinc. turn this off. What else do we have down here? Passivation. Okay. So next that gets us onto, so we have the bright nickel plating. So this is more of a decorative finish. It is not very corrosion resistant. It's not as corrosion resistant as the zinc, but it has a chrome-like finish. And you see these on like decorative fasteners. As you can see that this example they give you is an acorn nut, which is meant to be a finishing nut, and it's meant to look nice. I can tell you about the only things that I see these on, or see this coating on, is, you know, these acorn nuts and finishing washers. They're really very few applications for the nickel plating because it really just doesn't provide a lot of mechanical benefit. And finally, we have passivation of stainless steel. And I can tell you, I'm going to have to read this one again. So let's see. The passivation of stainless steel fasteners is the cleaning process for removing the contaminants of foreign particles sticking to the fastener from the manufacturing process. If the passivation is not carried out, then it will affect the corrosion resistance property of the stainless steel fasteners. Okay, so you can think of that like when you have something stainless steel and you end up, if you've ever used a grinder around a piece of stainless steel and then all of a sudden you get it wet, then all of a sudden your stainless steel is rusting and you're like, what's going on here? Well, the stainless steel isn't rusting. You're actually rusting the fine metal particles that have just embedded themselves onto the surface. And I actually believe they're having a problem with the Tesla Cybertrucks on this, where people said the panels were rusting, but it turned out what was actually going on is the metal surface was picking up iron debris, and then that was rusting. So that's something to keep in mind when you're using stainless steel. Okay, that is all I have for those. So I'm going to switch this over. So I'm going to go back to my little camera here. Let's see here. And we're going to talk about these fasteners a little more. So I'm going to go back to the self-threading here. And we already discussed these. Let's set these aside, see what I have next. Another self-drilling. This here's your the truss head. Now let's talk about that. Yeah, those are the truss heads. You can see two different tips. Here's another self-drilling. This one here, you can see that we have a longer drilling area on this one. So this one's actually made for thicker metal. You could probably actually run that into a piece of 1/4-inch plate. Bear with me on this camera. I have a better camera coming tomorrow. So I can lock in the focus. Here's another one that has the longer drilling section. And then I want to take a look at these here. It's going to focus on that. Doesn't appear so. Let's try this. Okay, well, I haven't had any questions today, so I think we're just going to call it for now. If you've been watching this, I'm going to try to do this every Monday, Wednesday, and Friday going forward. And if you have some things you'd like me to cover, just go to the website at rebel, REBELENG.US. And just shoot me an email and tell me what you'd like to see. And we will do this again on Monday.
Hey everybody, before we dive back into today's engineering discussion, I just want to take a moment and say thank you for being here. If you found value in this engineering question and answer session, the deep dives into design, manufacturing, and everything else we explore here, first off, I'm glad you're getting something out of it. This community is all about curiosity, critical thinking, real-world problem solving, and I'm honored to be part of your journey. If you've enjoyed the content and want to support the growth of this channel, one simple and powerful thing you can do is follow or subscribe, or whatever your platform calls it. Whether you're watching on YouTube, LinkedIn, TikTok, or somewhere else, that follow means a lot. It helps more people come to discover this content, and it tells the platform that we're doing something here that matters. Now, if you're finding this useful and you'd like to go one step further, maybe you want to help improve the quality of the show or make it possible for me to produce more detailed, better researched, higher quality episodes, then I truly appreciate your support through donations. You can head over to rebel.us/support. That's rebel.us/support, where you'll find links to Patreon, Buy Me a Coffee, and PayPal. Every bit helps, from covering the cost of gear and software to freeing up more time to prepare better content and answer more questions. And while you're on the site, you can also reach out if you have a project you'd like to talk about, a topic you want to see covered in future episodes, or if you're interested in partnering with me in some way. This is a growing collaborative space, and I'd love to hear from you. Thanks again for being here and making this community what it is. Now back to the